So let's just really quickly, I did some of it already, but I want to just write this down, is to review some of the periodic trends. And then we're going to apply it to a lot of different things. And then we're going to draw one more trend. We'll talk about the trend in orbital diagrams of the d orbitals. Okay, so, but the effective nuclear charge is one of the things that we have to look at when we're looking at trends in transition metal elements. But the other thing is, because you're putting 10 electrons in, there's some effects that you get that you only see in the transition elements and the intertransition elements because of the number of electrons that are present in the d orbitals. So if we think about how you expect ionization energy to behave on the periodic table, you could draw a little periodic table like this and then make some notes on it. Going this way, Z effective is increasing. So what's going to happen is you would expect the ionization energy to be higher on this right-hand side of the periodic table. Also, when you're going up in this direction, right, you expect it to get higher because these are closer to the nucleus. We see the same behavior in radius. And so in radius, what we'll see is the radius will get smaller as we go this way. And then because Z effective is increasing going like this, then we expect that the radius will be getting smaller. But that actually means something different for density, okay? So for density, what we expect, at least going from left to right, is we expect, because the radius is getting smaller, we expect them to be more dense. The reason being, right, they're getting smaller, one, but also because you're adding mass into the nucleus. So we have two things that should increase the density of the element. And then lastly, as you go up in this direction, well, they're a lot less massive here and a lot bigger down here. So there's actually two things that are going on that sort of counteract each other. But in essence, because you're adding more mass relative to the radius, then it ends up they get denser as you go down in the group. So radius gets smaller, but mass is getting bigger. And there's no good way to tell which one's more important, so you just have to remember that these are more dense at the bottom. And denser to the right and more dense towards the bottom. Okay, the last thing we're going to look at is we're going to look at the trends in electron configurations of actual atoms, right? And not how we expect them to be, but how they actually are. Okay, so I'm going to kind of wing this, but this is some crude orbital diagrams. I put a vertical line to separate the S's and the D's, because we need to look at the S and the D orbitals. And we're just going to do the fourth period. So this first one is scandium, so this is Sc, and it has two S electrons. It's the first one to put electrons into the D orbitals. So then we have titanium. And then we go like this, and then we have vanadium. And then we have chromium, and chromium is the first point where we have an exception. And what's going to happen is we're going to put one electron in here, chromium. We're put 4 electrons here. Well, actually what we're doing is we're taking the one electron from here and then promoting it here. And this gives us that orbital symmetry that we talked about. And then we go to half-filled, which would be manganese. So manganese would be like this. And sorry, just realized I forgot. Then we're on to iron. So we have iron would look like this. And we have to pair one finally. And then we're going to go like, oops. And we'll pair two. And then we're going to go like this. And we're going to pair three. And then what we're going to do, we have, again, our second exception, which will be copper. Oh, I forgot to write these in. Iron, cobalt, and then nickel. And then this will be copper, and this is zinc, which again isn't a transition element, but anyways, side note, right? This will be like this, except same thing that we did for chromium. Chromium, oh sorry, we're going like this. We'll pair up four, right? And then what copper can do, just like chromium can do, is can pull one of these s electrons out and pair. And so again, I have the whole orbital symmetry thing going on. The d orbitals are filled, and then the s orbital is half filled, so that helps in terms of stability. And then zinc, we have no options. They're all full, so we have all paired and no unpaired. So a couple of things I want to look at here. We're going to be looking at number of unpaired electrons. So this is unpaired. U-paired. You can put an N in there if you want. Unpaired. 1, 2, 3. All of a sudden you have 1 plus 5. Oh, I thought I wrote 3 here, but I guess I didn't. And then you have 5. And I just did this because you have an S and a D, but that's total 6. And then here we have 4. And then 3, and then 2, and then 1 plus the 0, and then we have 0. And just sort of notice what's happening. The most unpaired electrons happen at chromium, and then manganese, and for terms of d electrons, manganese and chromium have the same number, and then it begins to go down, 4, 3, 2, and then 1 and 0, and it's completely filling the d subshell, providing some orbital symmetry and stability because of that. Okay, so that's just something to keep in mind as we look at the properties of the transition elements. Okay, so this is a graph I made. I actually looked up all the data, mostly, if not all, for this particular graph. The data that I pick for all these graphs, for the most part, come from Wikipedia's. They have a nice little data section for each element now, and it seems to be fairly reliable and consistent. So most importantly, that's what I was looking for, stuff that was measured and defined the same way, and they're very good at doing that. So I went ahead and chose their data. Now, I've also have 3 sets of data on here. There's the 4th period, which is blue, which you expect to be smaller because it's energy level 4. Then there's the 5th period, which is bigger, and then the 6th period. And we'll talk about, you notice the 5th and the 6th are almost exactly the same size, right? And so what's going on there? But the general trend is true for all of the transition metal elements, 4th, 5th, and 6th at least, is we have largest to the left, right? And as you increase the effective nuclear charge, the radius gets smaller. Now, let's do a quick look back at our electron configurations, right? There's 1, 2, 3, and all of a sudden I have a whole bunch of unpaired, right? And then I still have a whole bunch of unpaired. And then the number of unpaired starts going down at the 6th element, okay? So 1, 2, 3, 4, 5, 6. Now, what's happening here is I'm pairing more and more electrons in these orbitals. And the electrons have a repulsive effect on each other. So, going from left to right, oh gosh, hang on. Has a mind of its own. They need to get the controls, and Microsoft needs to get the controls off the bottom down here because you're hitting them all the time with your hands. Anyways, right, going from left to right, like here, what's happening is effective nuclear charge is going up. So this is caused by Zeph. More attraction to the nucleus, they get smaller. Then what happens is you start pairing up electrons. So this is what's attributed to something called electron-electron repulsion. So we have two things going on, right? We're pairing electrons. And that pairing causes the repulsion of the pairs to go up. And as a result, they have to get further away from the nucleus. And so we have this sort of shrinking from left to right. And about halfway through, it begins to go back up again. But you can easily attribute that to pairing of electrons. Now, having said that, right, there's something called the lanthanide contraction. And I'll explain that to you. You notice this is energy. Blue is the fourth period. Red is the fifth period. And as you'd expect, this is going from 3D to 4D, right? So the 4Ds you'd expect to be bigger, so that totally makes sense. But then the sixth period you'd expect to be bigger as well. But it's actually not. It's about the same size. Certainly with the way they measure radius, it's kind of, there's a lot of different ways you can do it. Essentially, they're the same. So what's happening here, though, is something called the lanthanide contraction. So the sixth period introduces the 4f orbitals. Okay, so let's go back and look at our periodic table, keeping in mind fourth, fifth, and sixth period, right? So there's my fourth, fifth, and you notice what's happening here, sixth period, right? So like in terms of atomic numbers, there's kind of an 18 more here, but going to this row, what you're doing is you're inserting the f orbitals, and as a result, rather than being just 18 more here, it's way more. You added 14 plus 18. So there's a lot more nuclear charge here, attracting the electrons. Now we still have this general effect of effective nuclear charge and then this expansion, but between the fifth period and sixth period, we'd added 14 extra protons in the nucleus because of the lanthanides. And the result is those are much more strongly attracted to the center of the atom. Now, having said that, oh, and I made two graphs of this because I didn't know which one I'd like better. So if you like looking at that one, great. I just decided I'll just leave it in there for now. Next slide. No. So this is a graph of densities of element, and these are in grams per centimeter cube or gram per milliliter. So densities in units of grams per centimeter cubed, right? So water has a density of 1, right? These elements, osmium and iridium, are in the sixth period, so plotted backwards from the way that I showed you the others. These are, done with the third, fourth, fifth going backwards, right? But this is for density, and notice what happens. Because of the lanthanide contraction, you've added a lot of mass, but not very much radius, right? And so the result is the densities jump to 22, roughly 23 grams per centimeter cubed. I mean, to put that in perspective, a gallon of water weighs 8 pounds. If you had a gallon of iridium, it's closer to 180 pounds, 190 pounds. So it's a lot of mass, right? It's a very dense material. It gets used for a lot of different things, actually, because it's very corrosion resistant, medical devices and things like that. So the next trend to look at is melting points. And in general, right, what's happening here? 1 unpaired electron, 2 unpaired electrons, right? 3, and then 5, right? And then this is also 5. So this is, going back to our periodic table, the fifth column, 1, 2, 3, 4, 5. So this is manganese. This is the exception, right? And notice what happens to manganese's melting point. And this is not something that's normally pointed out, I think, but there's a big dip in the middle. And it turns out the big dip has to do with that orbital symmetry of the d orbitals and that stability that it gets. So what ends up happening is as it contracts and pulls those electrons in, it's not as good at making metallic bonds. Now metallic bonds have to do with the sharing of electrons, but the stability doesn't allow it to share as well. There's a lot of interpretations of this, and there's people that know far more about this than I do, to be honest. But that's what the general explanation is for these anomalies. The other thing to make note of is that if you're looking at fourth, fifth, sixth period trends, right, the electrons get held more loosely as you go to the larger atoms. You have better metallic bonding, and so their melting points go up. Now, when you go to more unpaired electrons, right, more unpaired electrons generally means better bonding between the atoms. As you begin to pair them up, they get smaller because you have fewer, right, unpaired electrons. And again, you go to the whole orbital symmetry idea. We get lower melting points, and this is in Kelvin over here. So this is mercury down here. It's the only element at only metal at room temperature that's a liquid, right? So that's way down here. I can't remember exactly what the temperature is, but it's very low. But same thing. You're pairing electrons up. Right? Unpaired electrons going in, pairing electrons going up. So the melting point generally goes with unpaired electrons. Except for when you hit the half-filled state with chromium, and that tends to, that's kind of like the exception. The stability of the electrons in a half-filled state means it's not as likely to share those electrons, and as a result its metallic bonding changes. And so the result of that is its weaker metallic bondings means lower melting points. But in general, everything else follows sort of an expected trend for unpaired electrons. Now, I almost don't like talking about this one. This one's kind of hard for me to understand. I'm sure it's hard for you guys to understand, but in essence, this shows the common oxidation states for elements in the fourth, fifth, and sixth periods. Let me change this to laser pointer. All right, and you get more oxidation states possible towards the middle. You get higher oxidation states possible as you go down, and the higher oxidation states for the sixth period occurs simply because, and the fifth period occurs simply because the orbitals, as you get further out, get closer together, so it's easier to have multiple oxidation states. Now, what are you looking at here, right? There's some red ones and there's some green ones. The red ones are the ones that are most common, okay? And the green ones are less common, but still possible. So you notice the only one that has only one in the fourth period, sorry, is scandium, and is, as you would expect for group properties, right? They all follow that same sort of group property trend. Most transition elements have a +2 oxidation state available, which would correspond to the removal of the s electrons and leaving the d electrons. Iron 2 and iron 3 are both very common, in part because iron 2 gets rid of the s electrons, and iron 3 gives us a half-filled d orbital electron diagram. So anyways, there's just the big takeaways from this is more oxidation states towards the middle, right? So we have more oxidation states in the middle. We have oxidation states at +2 available to all the elements, excluding primarily scandium, yttrium, and lutetium, and hafnium also doesn't have a +2, and actually I don't even know why the reason that is, to be honest with you. But again, most of them have +2 oxidation state, and more oxidation states toward the central part of the periodic of the transition elements. I've also sort of listed it in a different way, and I just sort of listed out for the fourth period, or the 3d orbitals. Next, we look at ionization energy, and for ionization energy, what happens is that the ionization energy generally increases going from left to right. So this is again 3b here, right? We generally increase effective nuclear charge. We generally increase the ionization energy. This is for the first ionization energy. If you remember, first ionization energy is when you have an atom and you convert it into its +1 ion, +1 electron. And this is known as the first ionization energy. And it's always a positive number that's endothermic. It always takes energy to remove an electron. And they're often measured in units like kilojoules per mole. And so another interesting thing that you see because of the lanthanide contraction, right, is that you see that the sixth period, or the 5d orbitals have electrons have much higher ionization energies, and that again is because of the lanthanide contraction. They're the same size but have a lot more nuclear charge, and so it just makes it harder to get the electrons off. There's also magnetic properties we need to mention, and so there's this idea of paramagnetic. For some reason I lost the word diamagnetic. And paramagnetic means attracted to a magnetic field. And B is a magnetic field. That's supposed to be an arrow. Sorry. And they measure that in something called the magnetic susceptibility. And elements that are paramagnetic are attracted to a magnetic field as a result of having unpaired electrons. The way they actually measure this, and there's some great YouTube videos on magnetic susceptibility, lots of common materials. Because rare earth magnets are so available, there's lots of materials that you can test for their paramagnetic and diamagnetic properties. Okay, so anyways, they're attracted to a magnetic field, and the way they actually measure it, or one of the ways it's measured, is something called a Gouet balance. And in a Gouet balance, they take a sample and they put it inside a tube, they seal it, and they balance this, and then what they do is they put it inside a magnetic field, and it'll either get pulled down, and so they can measure the force, or it'll get pushed out, and so they could also measure the force because it pushes the sample out of the magnetic field. So those samples would be diamagnetic. Diamagnetic, and they're pushed out of or repelled by a magnetic field. And these generally have all paired electrons. Now, the way it's measured, again, magnetic susceptibility, it's either attracted, right, or repelled. And if you look at the fourth period elements, I'm going to show you this and I'll come back and talk about ferromagnetic. This is a measurement of magnetic susceptibility. These magnetic susceptibility is going up because of the unpaired electrons. There's a lot of things. This is actually something that's really difficult to measure, apparently. I've noticed because it's not because it's hard to measure, let me put it that way. It's because it's hard to get really pure samples, and small impurities tend to affect the magnetic susceptibility a lot. Scandium, for example, can have impurities of hydrogen gas, which have big effects on its magnetic susceptibility. Other elements do the same thing. So these are paramagnetic, and the paramagnetism, the magnetic susceptibility, the ability to be drawn into a magnetic field increases as you have more unpaired electrons in general. And then if the electrons are paired, what happens is it becomes a negative number. So the magnetic susceptibility is a negative value. So copper and zinc have lots of paired electrons. These would classify as diamagnetic. So these guys are paramagnetic, and these are diamagnetic. That's actually, though, it looks horrible. Let me rewrite that. Okay, so, and then these, I just made them 0 because they don't classify the same way. These are known as ferromagnetic. And I'll talk about that on the other slide. But they have a special magnetic property. They can be magnetized, and they have interesting properties that make them that way. Now, you can make alloys of things that are paramagnetic and make them ferromagnetic. But again, of the pure elements, which are apparently harder to measure, this is what it looks like if you look up the data. I try to do more than the fourth period, but the data got real sketchy. One of the things is magnetic susceptibility is influenced a lot by temperature. And so a lot of times the values you get are at really, really different temperatures because they're trying to show something at that temperature. So anyways, I didn't have the references necessary to look it all up, but in general it kind of looks like this. Increasing susceptibility with unpaired electrons, decreasing or diamagnetic, right, susceptibility basically, with lots of paired electrons. Okay, so paramagnetic means within each atom you have unpaired electrons. So going back to this diagram, right, I just slid back to this slide, right, the magnetic susceptibility goes up with unpaired electrons and then starts going back down as you begin pairing them again. So this is what we saw. This is diamagnetic, and this one has a negative magnetic susceptibility and is generally classified as diamagnetic. Now, back to our original diagram. What happens is that's talking about individual atoms. When you have something that's ferromagnetic, what they do is the atoms within large regions of the crystal begin to align their magnetic fields and create these domains, they're called, where all the electrons are essentially spinning in the same direction in adjacent atoms. And this makes them magnetic. So when we're talking ferromagnetic, we're talking about a very different kind of property than paramagnetic and diamagnetic, because as a group they begin to align with each other. Okay, but again, you have to have unpaired electrons, and there's actually only 3 ferromagnetic elements. A lot of alloys, but only 3 ferromagnetic elements that exist, and that's iron, cobalt, and nickel, and everything else either classifies as paramagnetic or diamagnetic. So I'm going to qualify this graph. This is a graph, a lot of these graphs I made this year. I remade them basically by re-looking up old data. I'm not real happy with this data. There are some things, when you see things sticking out like this, that you question. Now I know they're supposed to stick out actually, but you question whether how accurate these numbers are when they stick out so much. And anyways, I'm still researching, so put some quotation marks around this slide. In general, let me tell you what resistivity is. It's the number of, it's how hard it is for electricity to pass through. Let's say you make a wire of it, right, or a rod of it, and you pass electric current through it. It's how hard it is for the electric current to pass through. And this actually is highest in the middle. This is really the whole reason I was doing this, is as you get unpaired electrons, and having unpaired electrons and more metallic character tends to improve the resistivity. That means makes it lower. But again, this is right manganese. It's number 5. And again, the orbital symmetry thing of having a half-filled d orbital and a full s orbital causes it to be a lot less prone to conduct electricity because its metallic bonds are weaker. That's what creates the whole thing. Now, mercury's resistivity is also kind of high, although it's still relatively conductive. Both of these are relatively conductive, but the resistivities are high again because of the d orbital symmetry stuff. These are higher down here, but then I couldn't verify all the numbers in the middle. It's really hard to find these numbers, so I wasn't sure whether or not I should use them. But the general trend is goes down as you go across, and then there's a couple of spikes up that have to do with, like these guys here, their electron configurations. Another reference I found is conductivity, and so high conductivity implies low resistivity, right? So what you see here is a conductivity towards this side. The electrons are better at moving, right? It's higher on this end, but again, chromium has got a high conductivity, but manganese again has a real low conductivity, just like that corresponds with its high resistivity. Anyways, it has to do with electron configurations, metallic bonding, and those properties. A couple other things. I like this table. I don't know if your book does it. It may have a separate chapter on it, but I just thought I'd include it because a lot of people go into engineering or interested in engineering. And alloys are actually solutions of metals or different elements. So sometimes the alloy includes carbon, but yeah, alloys are solutions of metals. And I thought I would just throw this in here because it lists some of the effects of alloying different elements with iron to produce different kinds of steels, right? So blended into iron, manganese, nickel, chromium, vanadium, tungsten, the typical amounts that they use, and then what effect that has on it. And it affects crystal structure, it affects electrical conductivity, how hard it is, how brittle something is, how flexible something is. So these are, and how corrosion resistant things are. And that's really one of the main purposes is of how we get like stainless steels, is we add elements in them to increase their resistance to corrosion.